Thank you always. Share. Okay. Can I see it?
Yep.
Okay, great. So this is the last class this semester. It's hard to believe, but that's what it is. So the first thing is about midterm schedule. And thank you for filling up doodle polls. So when we did the poll in class, it was pretty close. So that's why we need to have a recount or re-election. But it came out to be landslide elections. I don't think there's no room for contest. So we stick to the default schedule. So the official schedule for the final exam for this course is the December 18. So I post the problem set a week earlier than that. So December 11th, you have a week to work on it in the same way that you have done the take-home midterm. So that's decided now. Okay, so we'd like to finish up the QED and the Feynman rules today. So you've been working on this homework problem. So I hope you have now gotten how that works. So when you actually do the time-dependent perturbation theory, you bring down the interaction Hamiltonian, which turns out to be exactly the same thing as a part of the action from the exponent, which is in this time evolution operator. And so in this particular example of electron-proton scattering, I have one term for the proton field interacting with the electromagnetic field, another term, the electron field interacting with the electromagnetic field. And these Dirac fields extract basically the positive energy solutions out of the mode expansion, because when you expand out the Dirac field, it comes out to be the momentum integral of the annihilation operator of the particle times the positive energy solution. And I use the annihilation operator to annihilate the electron initial state. So part of psi, what that remains is this positive energy solution. The same way here, the positive energy solution with bar in it, positive energy solution here for the electron, positive energy solution for the electron and with bar on it. And then I use this propagator I talked about on Wednesday, and you have been working on the propagator for the complex Klein-Gordon field. So I hope you're getting the idea how this time order product or field operator works in momentum space. And when you do the spatial integrals, then at the end of the day, you find this overall momentum conservation as a result. But you also get additional constraint, namely that the full momentum you're supposed to use for this photon propagator is really the difference between the initial full momentum of the electron and the final full momentum of the electron, which is what we call the momentum transfer. So in some sense, there is this energy momentum conservation at this vertex. The amount of momentum that changed from initial state to final state is what is emitted as the full momentum of this, what we call the virtual photon. It is virtual because the Q squared of this photon is not zero. So that's the violation of actually energy conservation, because true photon with a full momentum given a spatial momentum has the energy given by the spatial momentum and speed of light. But this photon, if you work out the kinematics, carries no energy. So you're emitting the photon whose existence already violates the energy conservation. So that's the reason why this corresponds to the intermediate state we talked about when we discussed the Rayleigh scattering using time-dependent perturbation theory. So intermediate states may not respect energy conservation, and that's the meaning of being virtual. But in the Feynman rules, the full momentum Q has to be exactly the same thing as the change of the full momentum between initial and final electron. So each vertex conserved full momentum, both energy and momentum. But the existence of photon here with non-zero Q squared indicates that this is the virtual intermediate state. So that's the idea of deriving this Feynman diagram. Yeah, so any questions about this? You're working on this right now, I believe. We went through this on Wednesday, so it's not new, but anyway. All right, so I don't see any questions. So once you know this Feynman rule, then you can immediately associate this the Feynman amplitude. So here's the summary of the rules. When you have an initial state particle, you associate it with the positive energy solution. you have a final state particle, you associate it with the positive energy solution with bar on it. So dagger and gamma naught. So that's how we actually gotten this amplitude. So that's actually general rule. On the other hand, if you use the look at the antiparticle, we have to use the negative energy solution. And if you have antiparticle in initial state, you use actually the negative energy solution with bar on it, because it is the psi bar field that has the annihilation operator for the antiparticle. So that comes together with the negative energy solution with bar on it. So initial state particle is V bar. That's now the Feynman rule. And the final state antiparticle is V instead, without bar in it. So it seems as if this is V, which corresponds to psi. And so that's why we use the cyan color here. And that's why we use this backward arrow to indicate that this one for the particle is U bar, but this one for the antiparticle is V without bar in it, and hence the reverted arrow. So the backward arrow in time is not meant that the antiparticle is going backwards in time. That's impossible, but it's just a mnemonic, or the way you remember that the backward arrow always refers to antiparticle, forward arrow always refers to particle. And once you know which one is particle and which one is antiparticle, you know which solution you're supposed to associate with initial state and final state. And we talked about the propagator for the photon, which is 1 over q squared, basically, just like Klein-Gordon field, except that you have minus g mu nu in the numerator because the photon field has the Lorentz index. And then we talked about this vertex, which is given by minus e gamma mu when you set C and H bar to be 1 in the natural unit. In addition, sometimes you also want to talk about photon in the initial state or final state. For example, when you talk about the Compton scattering, then you associate the polarization vector for the photon, which we talked about when we quantized the electromagnetic field in Coulomb gauge. And for the final state, you associate the polarization vector with complex conjugation. So for planar polarization, it's real, it doesn't matter. But if you're talking about the circular polarization, you need to be aware that you have to put this complex conjugation on it. So that's something we also talked about already about a month ago. Sometimes you also need to have a propagator for the fermion field too. And I'll show you some example of that later on. So then you have this line for the fermion, and you associate this factor as a propagator. So this P slash is a new notation, which is just meant to be gamma mu and P mu with the Lorentz index contracted. So it's a matrix. Putting a matrix downstairs sounds strange, but if you multiply P slash plus M, both in the numerator and the denominator just becomes a number. This is not a matrix anymore. And this looks basically the similar thing as the propagator for the Klein-Gordon field, except that you have this P slash plus M upstairs. So that is what you're going to use when you have an internal line of the fermion connecting to vertices. So that's it. So this is the Feynman rule. So in principle, if you consider any process you like in quantum electrodynamics, then you first thing you do is draw as many diagrams as possible allowed by these rules. And once you have a diagram, each piece of the diagram, every line and every vertex corresponds to something very specific, as you see on this slide. And then you can immediately write down the amplitude of that process. So that's the very, very convenient and practical way of computing processes in quantum field theory. And of course, we are talking about QED here as a prime example of this. But the same technique would also work for the Schrödinger field in non-relativistic case. If you have some other interactions in QFT, you can apply also the same idea. The vertex may be different depending on what theory you're looking at. Propagator may be also different if you're looking at the non-relativistic field theory, but the idea is always the same. You have initial states, you have final states, you glue them together with the vertices. If you have an internal line, you put the propagator in there, and that's the way you can do perturbative calculation in any quantum field theory. So it's a very general idea. Here is a very concrete case of the quantum electrodynamics. Okay, any questions about this? Jose, are you trying to speak? No? Okay. Anybody else? Of course, I'm. Oh, go ahead.
I was just going to ask, what's the particular definition of P slash again?
So P slash is this gamma mu times P mu. So if you compare this line and that line, you see this P slash is the same as gamma mu P mu.
And that's a matrix or an outer product?
Yeah, it's a matrix, yeah.
Okay.
4x4 matrix. And this is a notation Feynman introduced, apparently. So he was a very practical guy. Any other questions? Okay. So let's look at a couple of examples here. Suppose you are looking at a process where you have electron and positron in the initial state, which is the particle and antiparticle. So they can actually annihilate and disappear from the world, but instead you have energy coming from this initial state, and that energy might materialize into a pair of particle and antiparticle, but different kind of particle, in this case a muon. And if you don't know what muon is, it is actually a particle that actually shines on you like thousands of them going through your body every second, actually. It's a cosmic ray particle. And so this is actually just a heavy version of the electrons, as far as we can tell, about 200 times heavier than electron with exactly the same properties. It's a Dirac particle, spin 1/2, same charge. I don't know why such a particle had to exist in nature. When the muon was discovered in cosmic ray, a famous Nobel laureate physicist, Isidore Rabi, actually complained. Who ordered that? Because apparently there was no particular reason why such a particle had to exist. But it does exist, and we can make them using this process. Namely that when electron and positron come together, using this vertex in QED, it can go into this virtual photon. And because muon has the same charge as electron, it has exactly the same Feynman vertex, so you can put them together using this vertex, and there's the Feynman diagram. So this is the process where electron-positron annihilate and briefly becomes a virtual photon. And this virtual photon now materializes into a real particle, muon and anti-muon. And we're going to actually compute this Feynman amplitude explicitly later on, but I hope you see that this diagram can exist. And the minute you see this diagram, you can immediately associate these different factors of the Feynman rules into this diagram and immediately write down this amplitude. So amplitude A is typically coming with factor of I for historical reasons. And then you see that you have initial state electron. So using this Feynman rule, I associate a positive energy solution with its 4 momentum P minus, so indicating this is for E minus. And then following the arrow, next comes this vertex, minus I gamma mu. And for this initial state antiparticle, I associated the negative energy solution with bar on it, with 4 momentum P plus for E plus. So that takes care of this side of the diagram. Then comes this propagator in yellow, that's this factor here. And then again, we follow the arrow for the muon side. So you start with final state antiparticle, that's the negative energy solution with 4 momentum capital P plus. Here is this Feynman vertex minus I gamma nu. And the final state particle is associated with the positive energy solution with bar on it for the 4 momentum capital P minus for mu minus, and that's it. So you can see that once you draw a diagram like this, you can immediately write down the amplitude for that process. And you know everything in here. We have solved the Dirac equation. You have the solution in some of the earlier slides. And also for the negative energy solution, you know what the gamma matrices are, and Q squared just the 4 momentum of this virtual photon. So you know everything in this factor. You can just plug them in, and out comes the Feynman amplitude. Then you can actually use the formula I'm going to tell you in a couple of minutes to compute the cross-section for this process. So that's the idea. So it's actually very simple, very intuitive, very practical. And then in principle, you guys can now compute any process you like in QED. In practice, it can get pretty tedious, and I can tell you more examples on, in this class today. But anyway, the idea is just this, and that's everything you need to know about how to do the perturbation theory in QED. Any questions here?
In terms of actually drawing the diagrams, are there particular things besides just having vertices and the arrows being consistent? Like, how is a conservation of energy or momentum enforced in these diagrams?
Yeah, so in this case, the electron flow momentum and positron flow momentum are added together at this vertex. So the flow momentum of this virtual photon Q mu is P minus plus P plus. And then this Q mu flow momentum turns into the flow momentum of capital P minus plus capital P plus. So as a result, P minus plus P plus is the Q mu, and Q mu is the capital P plus plus capital P minus. So at the end of the day, little p minus plus little p plus is capital P plus and capital P minus, and that's the overall flow momentum conservation of this process, right? So as long as you conserve flow momentum at every vertices, overall flow momentum conservation comes out automatically. So I didn't write flow momentum delta function here, but that is satisfied once you actually glue them together in a consistent fashion. Does that answer the question? Good.
Yeah.
Any other questions here? So as you see more, go ahead, Anna.
Well, I was just gonna ask, I just wanted to make sure, so like we have to write these factors in order as determined by like the arrows you were saying, or does it not matter?
No, you do want to write arrows. So the arrows indicate which line is meant to be particle, which line is meant to be antiparticle. So again, I'm following this convention, the time flows from right to left. So you see immediately that this E minus and E plus are in initial states because that's the rightmost lines. But given these arrows, I can tell that this is electron, this is positron. So in practice, you don't color lines, so they are all black and white, but you can still tell that this is particle, this is an antiparticle, because you can draw these arrows consistently. And arrows don't clash. Electron comes in, you cannot let electron annihilate with electron because then the arrows clash. So if you consistently assign arrows so that they flow constantly, then you don't make a mistake, like pretending two electrons can annihilate into photon. That's of course impossible. But electron and positron can annihilate because arrows don't clash and have a consistent Feynman vertex to go to this virtual photon.
I guess I was also wondering, like, just for the ordering of the terms in the like amplitude expression, if we have to follow the arrows like you did.
That's right. Right. So you always begin with the arrow coming into the diagram, and that's this U spinner here, and then vertex, and end with the arrow going out of the diagram. Of course, arrow going out in this case is still initial state in terms of time, but in terms of diagram, this is the arrow that goes out of the diagram, and that comes last. So you always follow the line of arrows for the fermions. You start with incoming arrow, you end with outgoing arrow, and keep everything in between. Does that answer the question?
Yeah.
And I hope it makes better sense when you actually look at the next example of E plus E minus annihilating into two photons. So here, this is a different process. Again, you have electron and positron in initial state. I have two photons in the final state. And now I need to figure out how to glue them together into a consistent diagram. So the first thing is that this electron now is connected to the positron using this internal fermion line. This is the first time you see it in use of this fermion propagator. And by using this internal fermion line, I can bring this photon to this diagram and using this Feynman vertex over here, again, you see that arrows are flowing consistently along these solid lines. And the second photon can be also brought together into this diagram using another Feynman vertex. And then again, you can immediately write down the Feynman amplitude by associating all the factors we talked about. So again, following this arrow of the fermions, you start with line with arrow coming into the diagram. So that's a positive energy solution for the electron. Then I have this vertex minus IE gamma nu. But here I have to also associate this photon with the final state polarization vector star. So that's the first photon polarization vector star, whose Lorentz index nu is contracted with this Lorentz index nu of this Feynman vertex gamma nu. So that's this vertex over here. Then comes the fermion propagator, which we talked about 2 slides ago. So this is the matrix downstairs, but it's actually a matrix upstairs instead. This is just a shorthand notation for it to basically save writing on the slides. Then comes the second vertex minus IE gamma mu, where mu Lorentz index is again contracted with this the polarization vector of the final state photon, second photon here with complex conjugation. And you end with this outgoing arrow from the diagram for the positron in initial state. So that would correspond to the negative energy solution with bar on it. So if you follow the fermion line, you always start with U or V, and you always end up with U bar or V bar. And that makes sense because after all, everything here is the 4x4 matrix. U is the 4-component column vector. V bar is a 4-component row vector. So that's the way I have the row vector, bunch of matrices in between, end up a column vector, and so that whole thing becomes a number. And that's what we want for an amplitude. Is supposed to be a complex number, as we all know from the quantum mechanics. So that's the way it works. So again, exactly the same ideas. The only new ingredient here is that I use this internal fermion line with this propagator. And this is the point I would also actually answer some of the questions I think Sahil asked before. So why don't we put label of positron and electron on each line instead of drawing these arrows? So remembering that this Feynman diagram actually sums already to time ordering between 2 vertices. It could be the case that this vertex is early, this vertex is late. So in that case, you're talking about the process that electron emits a photon first, and then keep going as an electron, then annihilates together with the positron to become another photon. So then this line is an electron. But if you think about the other time ordering, let's say this happens first. Then this is the case where positron comes in, emits a photon, then it has to keep going as a positron instead. And that positron annihilates with this electron to become the other photon. So this green line actually represents both possibilities at once, because it's a time order product of Dirac field and Dirac field bar. It has both possibilities in it. So I cannot label this line as an electron or positron, because the answer is, well, it depends. Depending on which time ordering that is, this line may be electron, this line may be positron. But the beauty of the Feynman diagram is that you don't have to worry about it. This is just the internal line. You associate this propagator, and you just keep drawing these arrows consistently. You don't need to ask the question, is this electron or positron? It's both, one or the other, but it doesn't matter. So that's the answer to, was it Sahil actually? I'm not totally sure. So what we don't label each line either as electron or positron specifically, but instead relying on these arrows for that reason. Arrows are consistent, but which line is electron, which line is a positron is not clear for internal lines for the propagators. They are clear for the external lines, but not clear for the internal lines because of this business of time ordering. But it doesn't matter. You don't have to worry about it because all you need is the consistent arrows, and you associate this propagator for every internal line in a consistent fashion. Okay, any questions about this? It's okay.
Professor?
Go ahead. Is it Andrew?
Oh, what is? Yeah. What is it? I'm a little confused about what is it on the vertex factors in the amplitude. What is it? Wait, what is it? Like, can you go over again why you lowered the indices on the gamma matrices?
Yeah. So this gamma nu has to be contracted with the polarization vector which you associate for the final state photon, right? And to contract two indices, one of them has to be upper index, another one has to be lower index to make Lorentz invariant contraction. So that's why I moved this upper index to a lower index so that I can contract the index nu between this Feynman vertex and this polarization vector. Is that okay?
All right, thank you.
Yeah. Okay. Any other questions on this example? Okay, but it turns out that for this process, this diagram is not it. There's another diagram. Because when you actually go back and think about how this diagram came about from the time-dependent perturbation theory, I have a mu operator here, I have a mu operator here, but a mu operator can create either this photon or that photon. They have different momenta. So there is another diagram where you interchange two photons and you have to sum it. So this is sort of something that looks similar to the symmetrization of the wave function you have done in quantum mechanics class. And of course, in QFT, as I emphasized already, there's no ambiguity, there's no choice, because this comes from time-independent perturbation theory with a mu operator creating a photon. You automatically get these two amplitudes from the time-independent perturbation theory. So this symmetrization is automatic. But when you draw Feynman diagrams, you have to draw two diagrams for each of this process. And for each diagram, for example, this internal line for the electron line would have different four momenta. So here I denoted one of them with four momentum Q, another one with four momentum K, because the four momentum Q would be P minus momentum of the first photon. That would be this four momentum Q. But for this diagram, I interchange them. So this momentum in the green line would be P minus for the electron four momentum minus the photon momentum for the second photon. And that is the four momentum K for this internal line. So, again, the idea is exactly the same. You conserve four momentum at each vertices, but because this epsilon 1 and epsilon 2 refer to a photon of different four momenta. So depending on which diagram you're looking at, you again assign four momenta for this internal line by carefully looking at this sequence of events of P minus, emitting a photon, and you subtract that four momentum to figure out the four momentum of this internal line, and so on and so forth. So that's the idea of E plus E minus annihilation into two photons. And let me emphasize here that this is the process you could never ever have talked about in quantum mechanics. Because as I mentioned earlier, quantum mechanics relies on Schrödinger wave function. Schrödinger wave function has fixed number of arguments. You can never talk about particles being destroyed or appearing. But this is an example where electron and positron inertial state just totally disappear from the world. And then instead you see two photons appearing. So particles annihilate, particles get created, and that's a process we can talk about in quantum field theory, but never ever in quantum mechanics. And now you see that in action. So this is an advertisement I did long time ago at the beginning of the class, and now you see this in action. This is the first time you're looking at the process where matter particle can really disappear from the universe. And it does happen. And that's the example, actually, you have seen in some of the slides I've talked to you, like the anti-proton coming into the photographic plate on the Berkeley Hills from Bevatron accelerator, which annihilate into a bunch of other particles. And you have seen a picture of it. Now you see how that is described theoretically in quantum field theory. Okay, any questions about this?
I just had a quick question about the
Right.
conservation. So you mentioned previously that the propagator or the virtual photon does not preserve energy or momentum.
Right.
But in this case, our four momenta are conserved at each vertex. So I guess I just see some sort of inconsistency.
Yeah. So I realize that's confusing because I'm using the word conservation in actually two different ways. So I apologize for this. So in this example, electron emits a photon, and for momentum of this green internal electron is indeed the difference between initial state electron minus the energy for the photon you emitted. So this vertex conserves all four components of momentum, namely energy and spatial momentum. So for momentum is conserved at this vertex, and when you do the formal problem, that conservation comes out automatically from the spatial integral. But the full momentum of this electron doesn't square to electron mass squared. So the energy of the electron here is not the momentum squared plus m squared square root. So that's what I meant, that internal line doesn't conserve momentum. It doesn't have the right energy for a given spatial momentum. So maybe I should have used a different word here, that when you actually have this internal line, for momentum is conserved, but you get wrong for momentum for the electron because energy and momentum don't satisfy the usual rule that energy has to be square root of momentum squared plus m squared. So instead of saying this line doesn't conserve momentum, energy and momentum, I should have said probably that this has the wrong energy and momentum. And that's the virtual electron. And if you go back a couple of slides, when we talked about electron-positron annihilation, and that's also the wrong for momentum for the electron, photon. So electron, positron come in, muon, anti-muon go out, you glue them together, and this for momentum of the photon is conserved in the sense that it is the sum of four momenta of electron and positron. But it is the wrong for momentum. If you actually look at this in center momentum frame, the electron and positron come head on with the opposite momenta, so the spatial momentum cancels, but energy sums up. So this photon has energy, but no momentum. So again, that's the wrong energy for a given momentum, which is zero in this case, because energy is not zero. So that's the situation with the virtual particle or internal lines. So in terms of Feynman diagrams, every vertex conserves four momenta, but internal lines from that conserved four momenta are wrong four momenta for that particle because the energy is wrong. It's not the right energy for a given momentum for this particle, and that's the case of the virtual particle. And that corresponds to this intermediate state we talked about in Rayleigh scattering some time ago. So I'm sorry for this confusing terminology, but did I clarify this question?
Yeah. So since it's a virtual particle, it doesn't obey the standard dispersion relation we normally have for a particle with some given mass or momentum.
That's exactly right.
Okay.
Thank you. Right. And so when the energy and momentum satisfies the usual relation, energy squared minus momentum squared is the m squared, then we say the particle is on shell. The virtual particles have wrong relationship between energy and momentum. Energy squared and momentum squared is not m squared. Then we say the particle is off shell. So being on shell is the right relationship between energy and momentum. Being off shell is the wrong relationship between energy and momentum, and the virtual particles are said to be off shell because of that. Okay? So going back to this slide, So here we talked about these two different Feynman amplitudes like this. And when you have a process where you have to interchange two fermions, as you can easily imagine, you actually get a relative minus sign. Again, there's no ambiguity. If you follow through the time-independent perturbation theory with operators, that minus sign comes out automatically because it's QFT, not quantum mechanics. You don't impose it, it's automatic. But in terms of Feynman diagrams, you still do have to draw two diagrams, write two amplitudes, and put the relative minus sign in between. So that's the basic idea. Okay, so now that we know how to, oh, go ahead.
I just
Anna.
had one question,
Go ahead.
which is maybe silly, but like
No
if we
questions are
want to
silly.
describe this like process of an electron and a positron annihilating and creating a photon, like why is it not sufficient just to have like one of our like vertex, like just like our like why do we have these two photons instead of just
that's a good question. Yeah, so as I said, there are no silly questions. So you can ask the question, why cannot electron and positron annihilate into a single photon? So electron and photon, let's imagine that both of them are at rest. Then electron for momentum is mc squared for the energy and 0 momentum because it's at rest. So if you put together electron and photon, electron and positron, total energy is 2mc squared and total momentum is 0, right? But for the photon, the energy has to be the same as momentum times speed of light. So it doesn't satisfy, again, the correct dispersion relation. So if the photon is virtual, like in the case of E plus E minus going to virtual photon and mu plus mu minus, you can go to single photon, but that's not a real photon. Therefore, it cannot exist in a final state. It is allowed to exist only within uncertain principle. In order to go to a real photon, it turns out then that the minimum number is 2. Then you can satisfy energy momentum conservation. So you have 2mc squared energy in the initial state, but no momentum. Then the final state photon has one of the photon carries energy of mc squared away, and it carries finite momentum mc. Then it satisfies the correct dispersion relation. And the other photon has energy mc squared and negative mc for the momentum, so that total momentum cancels to be consistent with the initial state 0 total momentum. And energy is also conserved now, and dispersion relation is also correct. So in order to satisfy both requirements, that the four momenta, namely energy and momentum, are conserved between initial and final states, but every particles are on shell, namely they satisfy the correct dispersion relation, then E plus E minus cannot go to a single photon, but can go to 2 photons or 3 photons. Does that answer your question?
Yeah, thank you.
Okay, good. Any other questions here?
I actually have, I'm sorry if I missed this when you were going over it, but when we write the Feynman amplitude for this process of E plus E minus to 2 photons, we're adding the terms in the amplitude. Do we always add them, or are we adding them there because the photons are symmetric when you interchange them? So like if we had fermions, would we subtract?
Yes, you're completely right. So I think I briefly mentioned this. So when you interchange 2 bosons, then there's a positive sign in between. When you interchange 2 electrons, for example, then you have a negative sign in between. For example, when you talk about the process of the scattering between 2 electrons, 2 electrons come in, and you exchange a photon in between, end up with 2 electrons. So then, for a given initial state 2 electrons, it can exchange and go like this, or can also be interchanged to go like that, and you write 2 diagrams, 2 amplitudes, but the relative sign between them is a negative sign in that case, because you're interchanging 2 electrons.
Okay, cool, thank you.
Okay, and again, once you actually go through the time-independent perturbation theory by sticking in operators, we know 2 fermion fields anti-commute, and that minus sign comes out automatically because of anti-commutation relation. So no ambiguity. It's not a sign you put in by hand. It comes out automatically. But when you do the Feynman diagrams, you need to be aware that the minus sign is there. All right, thanks for asking that question. Any other questions here? Okay, so now I hope you have gotten this idea, how you draw diagrams and how you write down the Feynman amplitude once you have the diagram, pretty much automatically now. And then the remaining thing you need to know is how to put this amplitude into a square and basically compute the probability. And that's the cross-section we already talked about in the case of the Rayleigh scattering. So we have this normalization of the creation annihilation operator given by 2 pi cubed 2e times delta function. And this is the Lorentz invariant normalization. And so in this case, we need to figure out how to actually take the square of the propagator, how you sum over the final states. And we also need to know the flux factor to divide the probability to obtain the cross-section, like what we did in the case of non-relativistic the Rayleigh scattering. So it's the same idea, but now that normalization is different, and it's not the box normalization anymore, so we have to figure this out a little bit more carefully. And the first thing you identify is that 2 pi cubed delta function in momentum basically has the meaning of space volume. So you may remember this from the Fermi's golden rule, where delta function in energy times 2 pi h bar could be replaced by the time interval. And that's how we obtain the probability of transition per unit time. So in the same way, the delta function in spatial momentum with 2 pi h bar cube has the meaning of spatial volume. So what that means is that in this normalization of creation annihilation operator, so this creation operator actually creates 2e particles in unit volume because of this normalization. So we are not using box normalization, so it looks kind of obscure and subtle, but basically that's the meaning of the normalization. So we need to be aware that we have 2e is energy particles per unit volume. And using that idea, the sum over final states for each particle also comes with 2e downstairs. So when we did this box normalization, we had v dqp over 2 pi h bar cube for one particle in the entire space. But here normalization is 2e per v, so you have to divide it by that. So that's why sum over final states would be dqp over 2 pi h bar cube over 2e, and this is the way you sum over the final states for each particle. So this is what is called the Lorentz invariant phase space. And then we also need to figure out the flux of the incoming particle because you divide the probability by the flux to get the cross-section. So if you're thinking about the scattering process where one of the initial state particles is at rest, then the density of the particle per volume is 2e, where e is at rest, then it's mc squared. Again, I'm setting c to 1. So initial state has 2n1 particle in it. So the flux factor should be inverse of this. And for the second particle, then that's moving and trying to hit the target. So this one is moving, so it's not rest energy, but includes the kinetic energy in it. So you divide it by 2e2 for the second particle. And to compute the flux, you want to understand how many particles come per unit time. So you also divide it by the velocity of the second particle. So this is the flux factor you need to compute the cross-section. But this expression is kind of inconvenient because it's specific to a particular Lorentz frame where one of the particles is at rest. So you would like to generalize this expression in a fully Lorentz invariant fashion. And end result is the expression I remember in the following form, 1 over 2s beta bar I, and S is the central mass energy squared, and beta bar I is a little complicated expression which depends on central mass energy squared S and mass of 2 particles in the initial state. So it's a little complicated, but this has a definite meaning. Because if you go to the center of momentum frame instead, then the center of momentum frame, it has a total energy squared is nothing but this factor S. And then in the center of momentum frame, both particles are moving. So this is the case of the collider experiments like the LHC. So each particle now has this number of particles 2e. So first particle 2e1, second particle 2e2, and then comes now relative velocity because both of them are now moving. And if you put them together, it does turn out to be the same expression at the end of the day because this is Lorentz invariant expression. And in this frame, this beta bar has a definite physical meaning. So roughly speaking, center of mass energy is shared between two particles. So roughly speaking, it's a half of it. The times beta bar is the momentum common for both particles because in the center of momentum frame, by definition, two particles come with the same momenta in opposite direction. So total momentum is 0. That's the meaning of center of momentum frame. So both P1 and P2 are given by the same number, and that number is where this expression beta bar appears. So the velocity of relativistic particle is P over E. And so the relative velocity is P over E for the first particle coming in. Velocity of the second particle is P over E coming in the opposite direction. So you sum them, that's the relative velocity. And if you put that into this expression, you can see that E1 and E2 combine with E1, E2 here and disappears. And then P is now rewritten in terms of beta bar, and that's how you can see this expression coming out. So the idea of using this expression, 1 over 2s beta bar I, which is not familiar to you probably, the first time maybe you have seen it, but this is an expression that's useful to remember because this is true in whatever reference frame you are in, whether you are in a lab frame where one of the particles is at rest, or if you are in the center momentum frame, you have the head-on collision in the middle. Either way, this expression of 1 over 2s beta bar I is true, and then you can write down expression for the cross-section right away. So this is a little technical stuff, but are there any questions about this?
I just had a question about the integral that you defined.
So this momentum integral.
Yeah, so is this counting the number of particles over k space or momentum space, or what?
This is counting the number of final states. So if you had done the box normalization a while ago, then in that case, the momentum were actually quantized by integer labels, right? Because you have to be in this box. Then you sum over those integers to sum over all possible final states of the particles. So that was a sum in that case. But if you take the infinite volume limit, then we figured out that the sum of the final states is the same thing as spatial volume times momentum integral over 2 pi h bar cubed. So that's what we discussed already a while ago. So this integral is what corresponds to that. So instead of summing over the final states for discrete momentum modes, we have continuum because we are looking at the infinite volume limit. But we have this weird normalization with 2e factor in it. So that's why the sum over the final states need to be done with this integral instead of the sum over the integer modes of the momenta in box normalization. Does that answer your questions, Hill?
Yeah, I guess I'm just confused about this interpretation of having 2e particles per this volume defined by a delta function.
Right. So this 2 pi h bar cubed delta function, roughly speaking, has this meaning of the volume in the same way that in Fermi's golden rule, 2 pi h bar times energy delta function had the meaning of time interval. So this thing here is basically volume. So AA dagger is not 1, but it's 2e times volume. That's what this is saying. That's why A dagger A is the number operator, which comes with a normalization of 2e times volume. Hence, you have 2e particle per volume using this normalization of creation-annihilation operator.
Okay, that makes sense.
Okay. Any other questions? So again, you don't need to remember this argument at all at the end of the day. All you need to remember is that sum of the final states is done with this Lorentz invariant phase space. And then the flux factor is given by this 1/2s beta r, beta bar I. So if you put all of these things together, here it is. This is the master formula. So you have this Lorentz invariant phase space for whatever final state particle you have. So in this case, I'm considering 2-to-2 scattering process. So I have only 2 particles in a final state. If you have more, you just stick in more integration volumes to it for each particle. It's always d cubed p over 2 pi cubed 2e for every particle in the final state. And then comes this Feynman amplitude absolute squared for the probability. And then you have this delta function for the overall full momentum conservation. And then comes this flux factor of 1/2s beta bar we just talked about. And that's it. So the idea is that once you draw a Feynman diagram, you know immediately how the amplitude looks like. And once you compute the amplitude, you stick it into this absolute square because it's just a complex number. And that's how you get the probability. And then you sum over the final states using this Lorentz invariant phase space together with this full momentum conservation, and divided by this flux factor 2s beta bar I, and that's it. So this is the way you can compute cross-section for any process you like, once you know the Feynman rules, and once you know what the Feynman diagrams are. So that's the idea. And so the Feynman diagram is a very practical method, very intuitive, very useful, and then you can go ahead and immediately compute any process for the scattering cross-section using this master formula. Any questions about this? So I hope that gives you a better answer to your questions, Sahil. How are you using this sum over the final states in a practical fashion?
Yeah.
Okay, good. Any other questions? So you will see this in action in a couple of slides. So hopefully you get a better idea on what's going on here. No questions? Okay. So, but this master formula still looks a little messy because of the delta function. And it turns out that this 6-dimensional integral, that sounds formidable, but together with 4-dimensional delta function, is after all just 2-dimensional integrals, right? And you can drastically simplify it. So, and that is actually done in my lecture notes phase-space.pdf. And that's a new lecture note I put up on the B courses, so please look at that. So there, the calculation is shown very explicitly. But at the end of the day, this 6-dimensional integral with 4-dimensional delta function just becomes this solid angle integral in the case of the center momentum frame. So when in the center momentum frame, 2 particles come in and 2 particles go out. So basically, the only thing you need to know is in which angle in the solid sphere the final state particles go, and that's given by this solid angle integral. So it turns out that that's it. And there's an overall normalization here, which is given by now beta bar f. So this is the same expression as beta bar I, except that I have to put in the masses of the final state particles, which are labeled by M3 and M4, but same analytic expression. And this beta bar f over 8 pi is the overall result of this phase space integral. And then you still need to take care of the solid angle dependencies of the amplitude squared, normalized, of course, by 4 pi. So for simple case of elastic scattering, then initial and final state particles are the same. So M1 is same as M3, M2 is same as M4, because beta bar I and beta bar F are the same analytical expressions. If the masses are the same, they are really the same. So beta bar F coming from the phase space integral and beta bar I in the flux factor cancel. So this case is really simple. Cross-section is 1 over 16 pi s. Again, s is the center of momentum energy squared, and solid angle integral of the Feynman amplitude squared, and that's it. So using this expression, we will look at the electron-proton scattering again, and also E plus E minus annihilation into mu plus mu minus once again, and actually get the cross-section. Then that's a physical observable you can compare with the data. So that's the idea of this, the cross-section, how to actually work out the cross-section using Feynman amplitude squared, and the phase space integral. And for elastic scattering of the 2-to-2 process, it's particularly simple. Okay, any questions about that?
Oh, I think that maybe the slides got cut off. Like,
oh, really?
I think the formula for the simplified integral got cut off.
This one with omega?
Yeah.
This just ends with d omega over 4 pi. There's nothing further right.
Okay, okay.
Yeah, so this is really the end of it. I tried to squeeze it in. Any other questions? Yeah, again, once you see this in action, you get a better idea. So let's actually get to an example. So by the way, this is my PhD thesis. So when you actually do these Feynman diagram calculations, when you go to a little bit more complicated process of not the 2-to-2 or 2-to-3, 2-to-4, and so on, very quickly, you find many diagrams. You can work them out by hand. You have to rely on some numerical techniques. So I actually wrote a software package to compute the Feynman amplitudes for any quantum field theory by gluing these internal lines and vertices and so on as a package. And I call that HELAS, which corresponds to helicity amplitude subroutines. Then later, this was automated and became the engine of a bigger package, which compute any process in a standard model automatically. And that package is called MADGraph. So MAD in this case is not MAD, but this is actually written by people at Madison University of Wisconsin. So that's why this is MADGraph. But anyway, so if you actually look it up, you can find the software package, you can install your computer, then you can compute any process you like in the standard model on your laptop using this package. So that was my PhD thesis actually. And the reason you have to rely on numerical methods is the minute you talk about, for example, 2-to-3 body process, you already have 8 diagrams. If you go to 2-to-4, you may have this many diagrams. You can't possibly do this by hand anymore. So that's why you have to rely on some numerical techniques. And this is the way you actually do the computation for more complicated processes. So today in class, we only look at very simple cases where we can do things by hand so that you get an idea how things work. But in most practical situations, you do have to rely on some other numerical packages to actually compute the Feynman diagrams. So you just need to be aware of it. So we are only looking at the simplest examples possible, but in practice, you may have to do something different because in most cases you can do this by hand. All right. And by the way, when I actually wrote my PhD thesis using this software package, I nearly failed my thesis defense. Back in those days, people didn't appreciate how complicated these calculations can be. So the theorists on the committee said, well, this is not theory, it's just a computer program. Experimentalists on the committee said, well, this is data, but not experimental data. So, there was a huge argument apparently on the committee if this was worthwhile PhD. I nearly failed. Fortunately, there was one professor on the committee who defended me. So here I am with PhD, and I am professor of physics. So, I almost missed it. So that's something, it might happen to you, so just be aware of that. Okay, so now that we are now equipped with all the tools we need to compute the actual cross-section, so let's see that in action for the electron-proton scattering. We already figured out what the Feynman diagram is. And for this diagram, we could already figure out what the Feynman amplitude is. So the only thing then you need to put in is this positive energy solution U, right? And that's all you need to do. So let's say we do this in the limit of non-relativistic situation. And then in a non-relativistic situation, the positive energy solution simplifies because in the non-relativistic limit, Energy is basically mc squared. You can ignore the kinetic energy, which is suppressed by 1 over m. So second piece here is gone. You only have the first two components with a normalization given by square root 2m, which is mc squared plus mc squared. I set c to 1 as usual. So that's particularly simple. And because you have only upper two components, when you look at this combination of u bar, gamma nu, u, gamma matrix for spatial components is off-diagonal block. But for off-diagonal blocks, upper two components would go to lower two components, which is 0, so they disappear. So the only thing that survives is actually the time component. And u bar is u dagger gamma naught times gamma naught. Gamma naught is 1. So all you need to do is compute u dagger u, and that's this combination over here for proton line or electron line. So this is particularly simple in this limit because for the electron line, only the time component survives, which is minus IE from this Feynman vertex times 2m, that's this normalization squared, and final state two component spinner dagger, initial state two component spinner. You can choose the helicity eigenstates as we have been doing, but you don't need to do this because in non-relativistic limit, the spin is approximately conserved, right? So you have done the homework problem where you have the finite momentum, then spin is not conserved. You have to make sure that you look at the total angular momentum together with the orbital angular momentum. But when P vanishes, Hamiltonian for the Dirac operator is mc beta, and beta commutes with sigma, so spin is conserved. So I can take this initial state to be spin up. Then the final state is also spin up because of the inner product. So you can forget about spin degrees of freedom as well that way. So everything becomes very simple. Same thing is true on the proton side. So u bar gamma naught u gives you IE with the opposite sign because proton has positive charge to capital M for the proton mass, which is 2,000 times bigger. So I'm using capital symbol for that. Again, spin is conserved. So I can set the spin wave function to be 1 just by assuming that spin up came in and spin up going out, then chi dagger chi is 1. So I can forget about the spin degrees of freedom. Then I know everything in this Feynman amplitude. So amplitude, especially in the limit where proton mass is regarded to be much larger than electron mass, which is true, 2,000 times bigger, then I can forget about the recoil on the proton side. Then kinematics also becomes simple. Initial state electron comes with velocity v. Final state electron also goes out with velocity v, but in some off direction after the scattering, which I describe by the solid angles by spherical coordinates. And then momentum transfer of this virtual photon. Again, I have to conserve full momentum at this vertex. So the q mu is the same as pi minus pf. Well, I use pf minus pi rather here. And so then it can be written out explicitly. But the only thing I need is this q squared, namely time component squared minus spatial component squared. So I can immediately compute what q squared is, and that turns out to be this. And for some historical reason, people often write this using sine squared theta over 2 instead of 1 minus cosine theta. So that's the q squared. So now I know everything. So this piece here for the proton line, that's this IE to m. This piece here along the electron line, this is minus IE to little m. And then I have minus I G00, because both of them are time component. G00 is 1 over q squared, which is given by negative 4m squared v squared sine squared theta over 2. So I know everything about the Feynman amplitude. Then I put that into the master formula for this very simple 2 to 2 case, which we worked out on previous slide, and out comes the cross section. So that's what I'm going to do on the next slide. Any questions about this?
How exactly was Q derived again?
Yeah, so Q mu is you have to conserve 4 momentum at this vertex. So the Q mu, if I view Q mu coming this way, is that Pi plus Q would equal Pf. So Q then is Pf minus Pi. So here's the Pf, here's Pi. So I subtract Pi from Pf. That's why time component vanishes. So Q mu doesn't carry any energy. And for the spatial components, this minus 0 is this piece here. I factored mv up front. For the y component, this minus 0, again, is this piece here. I factored mv. For the z component, I have mv cosine theta for the final state, but mv in the initial state, that's why I end up with cosine theta minus 1 times mv up front. Does that answer your question, Sahil?
Yeah. You just applied it to the electron-positron vertex.
That's right. And if you do this on the proton side, you again get the same answer because you conserve 4 momentum at this vertex, you conserve 4 momentum at that vertex, and everything turns out to be consistent with 4 momentum conservation between initial and final states. Okay? Any further questions on this? So now you're seeing everything in action. All the ideas we talked about the QFT this semester is now coming into something really practical you can use to compute these scattering processes. Okay, so now that I have this Feynman amplitude now already worked out, I just put that into the master formula and get the cross section. So here is the amplitude, which we computed. So Q squared is downstairs. That's why sine squared turns into cosecant squared. And I square this Feynman amplitude to put that into this simple master formula for the cross section. So you have this solid angle integral. So differential cross section d sigma d omega then comes out to be this. And S is a center of mass energy squared because both of them are non-relativistic. Center of mass momentum, center of mass energy is just sum of the two energies, mc squared and mc squared for electron and proton. You square that. We are in the limit where little m is much smaller than capital M. So this is approximately capital M squared. That's this plus factor over here. But Feynman amplitude has capital M upstairs, so that gets squared. So capital M dependences cancels out. The only mass dependence then is actually mass of the electron. So it's basically that if you actually retain both masses correctly, this m is the reduced mass of this little m plus capital M system. And then you find this dependence of cosine second or fourth, the theta over 2. And if you recover C and H bar, it turns out for this formula, the C and H bar is not needed to get the correct mass dimension. Only thing you need to put in is this not magnetic permeability, what's the name of it? Permissivity of the vacuum. And that's the only thing you need to provide to get all the units back. And once you do this expression, you might say, oh, this looks familiar because this is exactly the same expression for the Rutherford scattering you have worked out in classical mechanics class. And this is a new revelation. So classical E&M, we talked about forces in classical E&M and solve the Newton's equation and work out the cross-section and comes out this Rutherford scattering formula. But classical E&M is actually obtained by exchange of a virtual photon. So what we think of forces in classical mechanics are now discussed in quantum field theory as an effect of exchange of virtual particles. So given this idea, we say photon is a force carrier of electromagnetism. Rutherford scattering, of course, happens because of the Coulomb force between electron and proton. And we now understand the Coulomb force as a result of exchanging virtual photon. And that's the way QFT describes a force. And this turns out to be fairly general. When you talk about the weak force, which is responsible for the nuclear beta decay, you exchange a different particle called a W boson, or weak boson, so W stands for weak. And by sending a virtual W boson, you mediate the beta decay of neutron into proton, electron, and antineutrino. We briefly talked about that. So force, which we learn in classical mechanics, is actually due to the exchange of virtual particle. Force comes with this force carrier particle. And for electromagnetism, force carrier particle is the photon. Exchanging virtual photon is the true nature of electromagnetic force. That is the description in QFT. But there's a little caveat. We worked out this Feynman amplitude at the lowest order in perturbation theory. So if the exchange of virtual photon at the lowest order in perturbation theory is what corresponds to classical electromagnetic force, higher orders of perturbation theory give you corrections on top of classical description, and that will be the quantum corrections to the classical theory. And you will see some examples of this quantum correction very briefly towards the end. But anyway, so this is a new idea. And this is quite natural in QFT, of course, because QFT is supposed to unify the idea of particle and wave. Everything is particle and wave at the same time. So that's the formulation built into quantum field theory. And everything that happens in nature then is described by sending particles back and forth, like in this Feynman diagram. And that ought to describe what we know already in classical theory as a limit. And here it comes. You do get the correct limit at the lowest order perturbation theory. So the Coulomb interaction, or in general classical electromagnetic force, is now described by the exchange of the virtual photon. That's a new concept, but we didn't have to put in this new concept. It just came out from the formulation of the quantum field theory. But I'm just emphasizing that we now have a new view on what we think of a force, very different from what we used to think in classical mechanics. Okay, any questions about this? This is a kind of philosophical point, so I'm sure you got questions about that.
This might be a little bit tangential, but
go ahead.
Is there a connection between like what order an electromagnetic effect takes, like what rank of susceptibility tensor we would need to describe it, and something about the Feynman diagram that describes it?
I'm sorry, I don't quite understand this question. So can you repeat that?
So if we have like nonlinear optics effects, a lot of them seem to have names that imply they would be described by more complicated Feynman diagrams, like two-photon absorption. But is there like some formal rule we can draw between like the rank of the susceptibility tensor associated with some nonlinear optics effect?
Yeah, so
Feynman diagram associated with it.
Okay, so nonlinear optics effect is definitely a quantum effect. So in the case of this, the electron-proton scattering, when end result end up not having any H-bar in it, right? So that's why this is the same as the classical result. But when you go to higher order processes, like in nonlinear optics, then you end up having other pieces which do depend on H-bar, because it's higher order in perturbation theory, and then you see that that's genuine quantum effects, which you don't have in classical description. Am I answering the question?
Yeah.
Not quite. Well, we do come back and talk very briefly about these high order effects and genuine quantum effects later on. So maybe you can ask the question at that stage. Is that okay, George?
Sure.
Okay. Any further questions on this slide? Now you see everything in action.
Just like physically, is there any interpretation of this virtual photon? I mean, I guess it makes sense in theory, but in terms of like physical reality, how should we best interpret it?
Yeah, so in some sense, electromagnetic field is a coherent state of a virtual photon. when you have for example, the Coulomb potential. The Coulomb potential is a static potential. But when you have actually particle moving, then of course Coulomb potential elsewhere cannot catch up because there's no information going faster than the speed of light. So information has to propagate from something moving to where you're measuring. So there is something actually moving from here to there. And that thing is actually the virtual photon intuitively. Does that make sense?
I see. So it's like I guess it makes sense. It's like the carrier that sends that Coulomb potential to another
That's
location.
Right. So the virtual photon is carrying information about how the other stuff, for example, when proton is moving here, then the electron gets affected by it. So you need to send that information using virtual photon from proton to electron so that electron knows how it should get scattered as a result.
Oh, I see.
So that's sort of the intuitive picture of this.
Mm-hmm. Yeah, that makes more sense.
Okay. So let's look at the other example of this electron-positron to mu plus mu minus. And in this case, I take the opposite limit of the massless electron and muon so that I can forget about mass terms. And then again, the spinors simplify. And four momenta also can be written in a very simple way in a center momentum frame. Electron-positron come into the center from both directions. There's a collider experiment. And mu plus mu minus go out from the center in some off direction given by this polar angle theta. I took the frame where polar azimuthal angle is 0 just for the purpose of convenience. And then you can just put in these positive energy solutions, negative energy solutions as we described in the solution to the Dirac equation into this formula. And in this case, Q squared has energy but no momentum. Because if you look at the initial state, energy is E, momentum E for the electron. And for positron comes in the opposite direction, so momentum is minus E. So spatial components cancel, but the time component remains. That's the total energy 2E now. So the Q squared for the full momentum of the photon is 4E squared, which is nothing but the center momentum energy squared, which is the variable S I introduced earlier. So again, you know everything in this expression. You just plug them in and compute it. Here I decided to take particular helicity combination that particles, electron and muon have positive helicities. Antiparticles, positron and anti-muon have negative helicities. Then you just plug them in here and amplitude is very simple. IE squared 1 plus cosine theta. And you can understand this behavior 1 plus cosine theta because I chose this helicity combination that electron has positive helicity, right-handed, positron has negative helicity, left-handed. So if you look at this direction along the beam, the two spins add up. So there's a net angular momentum 1 along this direction of the beam. And from here, electron positron annihilate, disappear from the universe, and then out comes the muon and anti-muon. And again, I chose these helicity combinations. So there's again net spin 1 along the direction of the muon momentum. And theta is this angle over here. So initial spin 1 along this direction has the maximum overlap with spin 1 along the muon direction when this angle theta vanishes. But when theta goes all the way to 180 degrees, initial state has spin 1 in the positive z direction. Final state would have spin 1 in negative z direction. Then angular momentum wouldn't be conserved. That shouldn't happen. And therefore, amplitude vanishes when cosine theta is minus 1. So this behavior of 1 plus cosine theta in the amplitude makes sense from the consideration of the angular momentum conservation. So amplitude is very simple. Again, you stick that into the master formula, and out comes the cross-section. Any questions about this? I have to wrap that very quickly. Okay, so then I put that into the formula for the cross-section. And if you have the opposite helicity combination for muon, again, it's clear from this picture that I end up with 1 minus cosine theta instead. So when you compute the cross-section like this, yeah, you don't have the polarized beams typically. So you sum over both helicities of the incoming particles, you sum over both helicities of the final state particles. But because you sum, then you have to do the averaging over spin for the initial state. So that's 1/2 for electron, 1/2 the positron. You put all of these things together, and out comes the total cross-section. And if you actually retain the finite mass for the final state particle, then you have this beta factor. So in this case, beta really means the beta of the relativity, namely velocity over speed of light. And so it starts with beta, which means that when the total energy of the system is just enough to produce best energy of the particles, then velocity vanishes, cross-section vanishes. So cross-section rises from 0 as beta and start to saturate, and then eventually starts to go down. And this is an experiment data from an E plus E minus collider accelerator in Beijing synchrotron, and producing yet heavier version of the muon called a tau. And this is a third particle. So tau is meant to be tertiary, which is originally discovered across the bay at Stanford at SLAC. And so using this tau, which has a fairly heavy mass, even heavier than proton, you have this beta behavior coming in. This is something you can compute yourself if you retain the finite mass of the final state particle. And then experimental data and theoretical curves exactly match on with each other. And this is the way you can actually measure the mass of this particle called tau. So that's how you can compute this process, which you could never deal with in quantum mechanics because particles disappear, particles do appear, but now you can talk about this kind of process and you know how to compute the physical observables for that process as well. Any questions about this? Okay, so I apologize, but let me spend maybe 5 more minutes to go through what may be coming in the graduate level QFT, where you actually do study these quantum corrections George was asking about. It's not the same example, but something similar. But before going there, I'd like to show you that this process really does happen experimentally. And here we go. So electron beam is coming from your side into screen. Positron beam is coming from the other side of the screen to the screen. They meet right in the middle. And then out comes pair of muons. And this track means it's a charged particle. But it seems to penetrate all the layers of detectors to the very end, which means this is a very penetrating particle. And it has to be a muon. And so this is how electron-positron in your experiment really disappear from the universe and become a brand new particles named muons created from the creation operator in QFT, and you're observing that. And this is clearly different from E plus E minus going to E plus E minus, where electrons don't annihilate, because electrons shower so much energy in the material and they stop here. This is called electromagnetic calorimeter, and it doesn't go all the way to the end of the detector layers. So this is the case of the electron. So we know the previous picture is not electron. In the case of tau, it happens in a very similar way, but tau is an unstable particle that can decay fairly quickly within about a picosecond. So it happens within the detector volume. And what you're looking at is the decay products of taus. But once again, you have the very clear interpretation. And if you look at the angular distribution, that actually does match up with the angular distribution we worked out in the Feynman diagram. So these things really do happen experimentally. So let me just very quickly give you some upshots on what you might expect when you go to the graduate level QFT. So we talked about G factor being 2. Now that we learned that all the forces have to do with a virtual photon, the magnetic field is also a virtual photon. So G factor, you computed in your homework problem, basically corresponds to this diagram of electron feeling the external magnetic field, which is basically this virtual photon. But this is the lowest order perturbation theory, as I emphasized. if you go to higher orders, you have this process too, where you exchange virtual photon between initial and final state. And this is what is called the loop diagram, because you have a closed loop in the Feynman diagram. If you go ahead and compute this, it turns out the G factor is no longer 2. And I think Wendy was asking this question, that you heard the G factor is not 2 exactly, but there is a correction by alpha over 2 pi, disorder perturbation theory. And this is something you can work out. It's a definite prediction of quantum electrodynamics. And of course, this is the first correction at order alpha. There are further corrections at higher orders in alpha. And amazingly, some people do compute these things by looking at Feynman diagrams like these. It's amazing that some people actually compute these guys. But having done these computations, you get very precise prediction on the G factor of electron with an accuracy of 12 significant digits. And there is uncertainty in theoretical prediction, and that's because we don't know fine structure constant that well, which relies on experimental measurements. So if there were no experimental errors on the measurement of alpha, then you would have the theoretical prediction on a G factor with 12 significant digits. Also, amazingly, people have measured the G factor of electron with 12 significant digits, and within the errors in alpha itself, they all agree. Here is the difference between theory and experiment, relying on two different measurements of the fine structure constant, but both of them basically are 0 within the error, maybe 2-3 sigma error here, within 12 significant digits. It's incredible. This is the level of success you get out of quantum field theory. It's probably the triumph of the entire 12th century physics. And this kind of calculation is now still going on in 21st century. So QFT is really amazing and successful. So QED is the best physical theory ever. And that's why people came up with this acronym of QED, I believe. And these calculations have been pioneered by Toichiro Kinoshita at Cornell University. And he is now old and retired. And it is now carried on by his student, Makiko Nio. So he is the Kinoshita, so the karate master sensei. And his disciple, Makiko, is now carrying on to the next generation. And they are now looking at these 5 loop diagrams and so on and so forth. You have to use supercomputer for this. But anyway, so this is the level we can test quantum field theory, an incredibly successful theory. So here you see this example that classical electromagnetism is really the lowest order. You do have high order corrections coming from quantum effects, but they are predictive in perturbation theory, in quantum field theory, and they work incredibly well. Here's yet another example. I talked about Dirac equation in Coulomb potential, and one thing that was remarkable there is that energy levels depend only on J, so that you had exact degeneracy, for example, between 2s1/2 and 2p1/2. But again, because of this quantum correction with exchanging photon, now in the virtual photon given by the Coulomb field, electric field, it's the same diagram, but that actually ends up making the states not having the same energy by lifting up the S state just a little bit. And this difference in energies is what is called the Lamb shift, which was measured in radio. It turns out to be about 1 gigahertz. So this is another quantum effect. And the Lamb shift was measured right after World War II because an unfortunate history is that many physicists worked in the war by developing the radar, contributing to the military. So radar technology got very advanced during the World War II. And after the war, Mr. Lamb came back to his laboratory. And now with this new technology in hand using radar, he could actually measure this transition between 2p1/2 and 2s1/2. And this is again a quantum effects of the virtual photon exchange. And the last example we're going to talk about is that, again, this is the higher order diagram in electron-proton scattering. So this higher order diagram would basically make the fine structure constant not a constant anymore, but it changes as a function of the momentum transfer. So the strength of electromagnetism is measured at zero momentum in quantum Hall effect, for example. But when you actually measure the strength of electromagnetism at finite momentum transfer, the number turns out to be different, which you can also compute depending on whether Q squared is positive, time-like, or negative, space-like. You get different predictions, but asymptotically they look more or less the same. 1/137 is at zero for momentum transfer. But here's one data point measured at E plus E minus collider at CERN called LEP. And number is different, 1/129, as a cause of these quantum corrections to the strength of electromagnetism. Because electromagnetism, now we understand, is a consequence of exchanging virtual photon. Virtual photon can polarize the vacuum. This is called the vacuum polarization diagram, in a way that depends on the momentum transfer. So the strength of electromagnetism does change as a function of momentum transfer. And again, theory and experiment do agree. So that's yet another quantum effects that's coming when you take the graduate level quantum field theory class using these loop diagrams. So this is one example of the process called renormalization, which you will hear a lot when you go to the more advanced quantum field theory classes. Okay, so that sums up everything I wanted to talk about. I talked about these stuff first half, these stuff the second half. For topical material, I chose to talk about neutrinos being superhero who might have saved us from the complete annihilation, right? So that was a topical material. But now you see everything I have advertised at the beginning. So I said, you never see a photon in quantum mechanics class. Now you do see a photon a lot in QFT. And particle wave duality is built in QFT. Symmetrization, anti-symmetrization in quantum statistics is also built in, and you can deal with macroscopic number of particles without any problems using QFT formulation. This is a great tool for condensed matter physics. And you can now talk about processes where number of particles can change. We just computed electron-positron disappearing from the universe, leading into some other particles appearing. So you can talk about that process. And then relativistic QFT goes beyond quantum mechanics for sure. So now position is demoted from an operator to a parameter. Field is an operator instead, and gives new predictions like spin statistics theorem, G factor of the electron, 2 at the lowest order, corrections at the high orders. Existence of antiparticle was predicted by Dirac. It was confirmed by Anderson cosmic rays. We talked about CPT theorem. So we need this for really many, many different branches of physics. So that's the summary of QFT we talked about today. So I hope you enjoyed quantum field theory, and I hope you continue to study the subject at the grad school sometime in the future. Okay, that's it. Thank you, everybody.
Thank you.
Thank
Thank
you.
you.
Any questions?
Thank you.
I went over time, but I still welcome questions if you have any. Oh, you're welcome, Elijah. Okay, you're always welcome to send me emails or Piazza or B courses. So if you have any questions, just don't hesitate to ask me. Okay, have a good weekend and good luck with your exam.
Okay. All right.
Thank you again, Professor.
Thank you. Take care.
Thanks.
Thank you.
Welcome. Bye.